Okay, so let us start the class. So in this week, we will be discussing the assignment 5. Now, I'll be discussing the previous year questions of this assignment 5, which will, and also some concepts, which will help you in solving this week's assignment. Okay. Now, in this last year assignment or this year, what we have the topics are for this week. So let me write down the topics. So the topics are three-phase transformer. Okay. Then what we have is we will be seeing the various, what you say, vector group of transformers. Then we will see the Scott connection and open delta connection. Okay. So we will try to cover these theory questions. As such, the assignment questions are very easy. Okay. You just have to try to understand the class. It is very easy. Okay. It's a very simple and straightforward assignment. Okay. So let us start with the class. So here, let us start with the three-phase transformer. So as you understand that an n-phase system, like when I say three-phase, so like that there can be n-phase also. So an n-phase system is formed by n single-phase system. So it means that a three-phase system consists of three single-phase system. Okay. Then why we are going to three-phase? Why not single-phase? Why in our homes also the supplies are three-phase supply, or the power system generation and transmission is on three-phase? So we will discuss the things. So first we will start with the disadvantages or limitations of single-phase. Okay. So single-phase power contains double frequency harmonic components. Okay. Double frequency harmonic components, and noise is also high. Okay. Noise content is also high. Okay. And single phase machines have poor efficiency. Okay. Single phase machines have poor efficiency. Also, as you increase the number of phases, the power transfer capacity also increases. So the capacity of a two-phase system is root 2 times of single phase, and capacity of three-phase system 1.5 times of single phase. Okay, so we can see that so root 2 times is how much? It is 1.4 something. Okay, it's you can calculate the square root, so you'll get 1.41 something like that. So you can see that the capacity of three-phase system is higher than the two-phase and single phase. Okay, and also you will see that in a three-phase balance system, the third harmonic components gets cancelled. Okay, so the harmonics, the harmonic content in the three-phase system is, you will read. I will not go into much detail of this because this is a topic of power electronics. Okay, so harmonic content in three-phase system, like first of all you have fundamental, then on top of it you have fifth, seventh, 11, 13, and so on, 17, like that. So here all even harmonics are not there, even harmonics are absent, and triplen harmonics are also absent. Triplet means the third harmonic and its multiple, third, sixth, ninth, like that. Triplet harmonics are absent. Okay. So so in this way the noise content is low. The power, what you say, power capacity is also more. And if we go to like more number of phases, like 5 phase, like 7 phase, like that, even this further improves. However, the 5 phase and 7 phase system become more complex. So we have taken the, what you say, best of the both the worlds. Like we are not going into a lot of complexity, but also we are getting the advantages of having less noise or less harmonic contents, and hence the better efficiency. Okay, so that is why we go to 3 phase system. Now we will see the, what you say, this transformer. Okay, so let us go to this 3 phase transformer and the vector groups. So first of all, I have not discussed the polarity test the last week, so I will quickly write it down. Okay, so polarity test, though I'm discussing this for a single phase only, but I'm discussing this because I forgot to discuss it last week. Okay, so here, suppose you have a transformer like this. Okay, you have a transformer like this. So this is having a dot here. Now you want to find out whether the dot in this transformer is here or here. You are given a transformer with no markings. So how will you find out whether this is here or here? Okay, so for this we will conduct the polarity test. Okay, so what we do, we connect it like this. So for finding the dot notation, we have like this. So we basically connect the two windings, this primary winding and secondary winding of the single phase transformer. You can do it this way for the 3 phase also, because in 3 phase like this, you will have for the 3 phase. So in each of the individual phases, we have to find out the dot, what you say, notation. So we can do this series connection in each. So you can understand that this logic will extend to individual phases. Okay, so I'm discussing for single phase, and you can extend it to the 3 phase system also. Okay, now here we are connecting it with the series with the secondary winding. However, we have kept the, what you say, a voltmeter here, and then we have a supply here. Okay, okay. Sambit, I'm muting you, okay? Or you can mute yourself, okay? Otherwise, the noise, if you have doubt, then you unmute yourself and ask, okay? Okay. So here we have V dash, and then like this, okay? Now, this is in this way. Now, suppose the dots are like this. If suppose in actuality, the dots are like this. So because you have given a voltage supply in this way, so the plus sign of this AC voltage is suppose on the top, then what happens on the dot, the plus sign comes. Then because we know, like in the dot, like in if you see the lectures of the professor, you will see that he has discussed this thing, okay, in the first week, that in, if suppose if on this dot there is a plus, then on the other dot the plus polarity will come up. Okay, that is from the Lenz's law. Okay, so this plus is here. So what happens is that similarly this dot also sees the plus sign here. Okay, now you see this is like this, that plus, so it is like this, that this is a source like this, plus minus, then you have minus plus. So you can see that these two voltages are getting added up. So what will happen, this V dash, which is connected in the series combination, will become more than this individual voltage voltmeter reading V if they are additive. Okay, it means they are, you are this is basically like cascade kind of addition. So this is an additive polarity. Okay, So if this V dash reading, which is taking the reading of the series combination, sees the voltage more than the individual winding voltage, then these two, what you say, the series connected windings are in additive polarity. Okay, so this is how, so you see this is how we can see whether the, what you say, this dot is, what is the location of this dot. Okay, similarly for the subtractive polarity, what will happen? So for subtractive polarity, something like this will happen. Okay, so suppose you have a dot here. Now you have a voltmeter. Then you have an AC source. And then we are having a voltmeter which is connected in series, so it will measure the series connected reading. Okay, so suppose you are giving the plus here, so this plus will come here. Okay, as I have discussed that if suppose this supply voltage plus is applied to this dot, so the other dot will also see plus in this way. Okay, if the dot is up, so what happens? So in this case you will see that this V dash is less than V. Okay, because it is something like this. You can apply KVL here in this loop, and then you will see that, okay, this is basically these two are in subtraction, so that is why this is a subtractive polarity. Okay, so in this way, you can, if you are given a transformer, you can identify the location of the dot. Okay, if you are getting an unmarked transformer where nothing is written, so there you can recognize which the location of dot using the polarity test. Okay, so here I have discussed the polarity test for single phase. If it is a three phase, so in three phase what happens? This is the three phase system. So here we have individual R primary, R secondary, Y primary, Y secondary, and B primary, B secondary. So individually you can, on each of the individual phases, you can connect them in series, and then you can apply this polarity test in the individual phases to get the dot locations in the three phase system also. Okay, like that. Now we discuss the phasor groups. As I said, I'll discuss the vector group or phasor group. So let us discuss what is this phasor groups. Okay, so here I am following the British code. Okay, there is an American code and there is a British code, and we generally in India we follow the British power system, what you say, this rules regulations. Okay, even the frequency you see in the American or these other countries, you will see this, the frequency is 60 hertz, but we follow the European grid format. Okay, so they have 50 hertz. So similarly here also the various terminologies like vector groups, phasor groups, and how we are categorizing these transformers we have adopted from the British system. Okay, so we are following the British code of practice. Okay, for phasor groups. So here also we have the phase sequence is ABC. I'm writing the generalized thing, and then when we will use these things, you will understand the, what you say, what is happening. Okay, then this VAN, you will see there is a vector which we will be naming it VAN. Okay, is at 12 o'clock location. 12 o'clock means, you understand, right? When there is 12 o'clock in your house, in your clocks, so what happens? It shows like this, right? So it is this location of the, what you say, you can say the both the this your hour hand and minute hand of the clock, it is like this, right? 12, 1, then this is 11, 10, like this. Okay, so this, we are following the similar thing, like we will be, this is our reference vector. Okay, I'll discuss these things, but I'm just writing down the general rules. Okay, so that there is no confusion. Then we will see that the basically this capital I mean the primary or high voltage. We have kept the high voltage on this side. So this A means the capital A means high, okay, means the high voltage. If I write it as small, if I would have written it like this, then I would have meant the secondary side or low voltage side, okay. But for now I'm not discussing anything of this. We are taking the reference of the primary or high voltage side, okay. Then line A terminal. So from A to, what are these things? Do not worry, okay. I'm just writing it down so that when you go back to, after discussing the vector group, various vector groups, when you go back to it, there will be no confusion, okay. Then B A2 A1 is in phase with B A2 A1. Okay, what are these things? We will see. Don't worry. Okay. So that is now. Now here, what I want, another things which I want to write is, now I'll write the various phasor groups. Okay. So here we have group 1, which we will be calling as 0-degree group. Now what is in this 0 degree? We will be having y0, d0. Okay. Then Y means your, because this is a 3-phase transformer. So the 3-phase transformer primary side is also in star, secondary side is also in star, and also there is a 0. Okay, so I'll discuss what this 0 or 6, all these things mean. Okay. Actually, this is the terminology which even the because we have in India, we had adopted this. So in GATE also they follow the same terminology. Okay. So group 2 is 180-degree group. So here we have these vector groups. Okay, 6. Why? Because this is 4. So the clock hand, if you will see, so it is like this, right? So in a clock, we have 12 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so it can be drawn in a better way. So let me just give some space between 11 and 12. Okay, so this is the normal hour clock, right? So we will be following this clock system only here also. Now suppose I want to say dy1. Okay, so let me just write it, give you some example. Suppose I am writing what phasor group as dy1. So what does this mean? Okay, so this means from this, that HV, the high voltage side, because this is capital and the first letter, so HV is connected in delta, LV side is in star, it is in small letter, you can see. Okay, and then this is the phase of the clock. Now, what does this phase of the clock means? So as I said that the reference, the HV1, so this VAN is the HV vector. Okay, HV vector or reference. Okay, so this HV vector, we will place it at the 12 o'clock position. Okay, so this is at 12 o'clock. So this is 12 o'clock. And 1 means the location of this LV, some vector small VAN, like this is the location of capital VAN. So the LV voltage vector of A phase with respect to neutral, small VAN, location is at 1 o'clock, at 1 with respect to 12. So it is here. Okay, so this is small VAN. So this is the location and the angle is 30-degree. Okay, so this is what we mean by dy1. So similarly, if I am writing it as y0, so it means that HV is in star, LV is in star, and the phase of the clock is 0. So it means that if your capital this primary or high voltage side, what you say, A phase with respect to neutral, vector location is at 12, which is the reference, then the LV location is also at 12, because 0 means it is at location, there is a 0, what is a phase shift, okay? This is located at 0, because 12 is also 0, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it is also 0 hours. 0 hours or 12 o'clock. Okay. So like that. Similarly, YY6 means YY6, if suppose this is YY6. So this is what? This is HV is in star. LV is in star. And 6 means suppose this is my location of VAN vector, which is at 12 or 0 hours. So my this LV vector, basically the LV A phase vector with respect to neutral, that location is at 6 o'clock. Okay, so this is at 6. So this is VAN. So this is basically, so here you can see this is 180-degree, right? So basically the what you say, the angle between the primary voltage and the secondary voltage is 180-degree. Here it is 0-degree, here it is 30-degree. Okay, so we will be seeing all this. So that is why these groups are categorized in degrees. Group 1 is 0-degree, group 2 is 180-degree, then we will see group 3 also. So group 3, which is 30-degree minus 30-degree or 30-degree lag. So 30 minus 30-degree, 30-degree lag. Okay, so here we have YD1. So lag means that basically the low voltage winding is lagging the primary winding by 30-degree. Okay, DY1. Okay, like this. Then we have group 4, which is plus 30-degree or 30-degree leading. Basically, so this angle which we are telling the location, because see, this primary or this primary or high voltage location is fixed at 12 o'clock or 0 hours. So whatever this angle, 0-degree, 180-degree, minus 30-degree, plus 30-degree, we are telling for the this secondary one, okay, this small VAN one. So that is why when I'm saying this is 30-degree leading, so the secondary one is 30-degree leading. So it means the YD11, DY11. Okay, because in that condition, it will be on 11 o'clock like this. So it will be 30-degree leading. Okay, so this is 30-degree leading. Is there any doubt in this? Whatever things I have discussed, these other things we will see when we draw the connection diagrams, but I hope this part is clear. Is there any doubt in this part? This is dy. Okay, this is dy. So this last one is dy, this one is dy. Okay, this is dy, this is dd. Okay, so you will see that whenever there is a star and delta connection, there will always be 30-degree involved. Okay, we will see that. Even when we draw the connection diagram, we will see that. So you will see that there is always a 30-degree phase shift between the star and delta connection. If we talk star, then there can be 0-degree or 180-degree. And if we talk delta, then there can be 0-degree or 180-degree. Okay, so because we are talking about star delta, so in star delta, there is always a 30-degree phase shift. Okay, so it is very important. So let me write this down. So this is very important. Okay, so whenever there is a star delta or delta star connection, okay, there is a 30-degree phase shift between HV side and LV side. Okay, okay, so this is very important. Okay, so you will see that is why in group 3 and group 4, which is 30-degree groups, we only have YD dy kind of delta star what you say transformers only. Okay, so let us quickly see some vector groups. So let us start with the zero group. Zero group is very easy. So I'll be discussing one in each of the group so that you will understand. Okay. So let me just draw y0 quickly. So we have y0. Okay. So in y0, so what I said, that the line terminals will be from A2. So what do I mean? So I mean this. Okay. So we have this phase. So we have 3 windings of the primary, and then we have 3 windings on the secondary of the transformer, right? Now we have to connect them in star. So I will name some things. Okay, so this is A1, this is A2, this is B1, this is B2, this is C1, this is C2. Okay, similarly here also this is A2, A1, B2, B1, C2, C1. Now, as I said, the line capital A terminal from A2. Okay. So when we are taking the line terminals of क्या कहते हैं of this high voltage winding, we have to take it from A2. So this is A2. So A2 we will be not shorting it. Okay. So A2 is the line terminal because we are taking the voltages from here. So where we will be connecting the star connection? We will be connecting the star here. Okay, at A1, B1, C1. So here also, so how you will know where? So because for YY0, for the secondary winding, where to do the star connection? How we will know where to do the star connection, right? You can do it at A2, B2, C2 terminals, or you can do it at A1, B1, C1 terminals. So let the dots be like this. Similarly, the dots are here like this. Okay, so where to do the star connection? To do the star connection on here or here for Y0? Okay, so what do you think? Where to do the star connection for Y0? Like just if on the dot side we have to short it, or on the other side we have to short for this Y0. What do you think? Remember the two voltage vectors. Like suppose this is the neutral point now. So this AN, right? So this VAN and this small VAN have to be in phase. Okay. So just think about it. So let us see, okay, how to do it. So let us see. So how we do it is, so we have our reference. So let us draw the, for this star connection, we will draw our reference vector diagram. Okay. So this I am exactly drawing like how we draw in our what you say 3-phase systems. We have the phase sequence, right? Phase sequence A or R we draw here. Phase sequence B is 120-degree lagging, so I am drawing it here. Phase sequence Z is 240-degree lagging with respect to A, so this is 120-degree, and this is 240-degree. Okay, so I am just following that. Okay, as per the normal notation of the phase sequence, I have drawn this diagram. Okay, so I'm not writing it here. So here, so you can see that this is the A winding. So this is the A. So this is basically your this is A, this is C, this is B. So here we have A, here we have B, here we have C. Okay. Now here I'm drawing in the similar way, small a, small b, small c. Okay. We will see why I'm drawing this. You will get the idea. Okay. So this is like this. Now here, because the terminals are accessible here, and because you see we have shorted A1, B1, C1 here. So this is the A vector. Now A vector I am writing on this side A2 and on this side A1. Okay. Now on this side I am writing B2, on this side I am writing B1. On this side I am writing C2, and on this side I am writing C1. So you see this is a line like this. Okay, C2, C1. Similarly B1, B2. So you can see that on this point A1, B1, C1 are getting shorted just like in the diagram. You can see here in the diagram A1, B1, C1 are shorted. So in the in this phasor diagram also, when I'm representing these windings as vectors, A2, A1, B1, B2, C1, C2. So I have to draw it in such a way. I have to draw this diagram in, if you're drawing the diagram in such a way, then you will see that this will automatically happen, that this A1, B1, C1 will get shorted, like in the picture. Okay. Now, how to draw the vector diagram? So first we will, because this is a zero group, so we will first draw the vector diagram, and from the vector diagram we will decide where to short, whether to short it on A1, B1, C1 side or on the A2, B2, C2 side. Okay, so let us see. So now you see this is the face. Okay, so now what, for zero group, what needs to happen? So for zero group, okay, this also has to be in phase, right? This vector has to be in phase. So this is the vector, suppose VAN. So this is capital AN. Okay, so let me write, this is AN. AN and small an has to be in phase, right? So this is A1, B1, C1 or N. So this is N. So this is the vector. So these two vectors have to be in the same phase, right? Co-phasal, because this is 0 degree. 0 degree means co-phasal. Okay. So how will I draw it? I will draw it exactly in the same way. Okay. And here, what I am having? I am having A2, because this is the same 0 degree. So A2, A1, B2, B1, C2, C1. So you can see that here also the A1, B1, C1 has to be shorted, so that this phasor, okay, so this is the phasor. So I'm writing it as ABC. They are in phase. Okay, so you can see that this vector, basically this vector, suppose this VAB vector I'm drawing like this. So this is VAB. So this is VAB. So VAB here and VAB here are cofacial. Is it not? So that is why it has to be connected in this way. Now for this, let me write down some of the basic things. So first of all, what is the voltage transformation ratio? The volt, basically, so this is the voltage transformation ratio. Suppose this voltage here is V. So this is V by root 3. If V is your line voltage, so this is like this. Okay, so this is your star connection. So star connection is like this. So if you are applying V here, okay, so this becomes V by root 3. Okay, so these all things I am writing down here. So basically your first of all, this phase voltage ratio, transformation ratio is like this. So on this side you have V by root 3. On this side you will see that it will come out to be V by root 3 divided by 80, where 80 is this transformation ratio. Okay, so this is V by root 3 is to V by root 3 80, so that it becomes 80 is to 1. Okay, so whenever we are talking about this ratio, right, this we have seen in the previous class also, N1 is to N2. So how is this N1 is to N2 related? So this N1 is to N2 is this V by root 3 by, suppose on this side we have small v by root 3. Okay, so this will become small v by root 3. Okay, like this. So this is a ratio of what you say phase voltages. Okay, phase voltage on this side, phase voltage on this side. So for a star winding, if suppose we are giving line to line voltage as capital V, then the phase voltage becomes V by root 3. Okay, this can be derived. Like suppose you have, it is like this. So actually, I'm not going into that much of derivation of that, because that is the part of this fundamentals of electrical engineering course. Okay. So I'm just writing down these generalized things, because we have very shortage of time, right? We have to discuss these theories, and then we have to discuss the question. So it will take a lot of time. Okay. So you see, if so let me write down these things. So this is your star. Okay. And this is your delta winding. If suppose, so here, suppose this is your V line to line. So this is V line to line. Okay. This is V phase. Okay. So let me draw the currents also. Okay. So this is I phase. This is I line. Okay. So here also I will draw the same things. Actually, for discussing today's assignment, only this slide is enough. But I'm discussing the vector groups also, because that is a important topic in three-phase transformers. Okay. So like this. So here, this is V line to line. This is also V phase. Okay. And then this is your I line, and this is suppose your I phase. Okay. So for a star winding, star connection. Okay. So your V line to line is V phase by root 3. So how we can see this? Suppose you have VAB. VAB is line to line voltage, because this is between A and B phase, and phase is VAN. So V phase is VAN. Okay. So this is VAN. This is VBN. This is VCN. Now, if I have to see VAB, so VAB will be what? So let me draw it in a very clear way, so that you will also understand the angles also. Okay, so for that, I'm draw it clearly. Okay. This is your VAN. This is VBN. This is VCN. So VAB is what? So first of all, you understand that these angles are 120 degree. I hope this you understand. So that this whole thing is 360 degree. Okay. Now I have to calculate VAB. So what about VAB? So how will I do it? So VAB is VAN minus VBN. So I will be taking VBN. So I have to do is vector addition of VN and minus VBN. So here I will take the opposite. So I'll get minus VBN here. Okay. So you can see that this gets divided in 60 degree each. Now this VAN minus VBN, if you do, okay. So you can do the vector addition. So you will get a vector here, which is VAB. So this VAB is leading VAN by 30 degree, and if you do this addition, na, if you do this, what you say, if suppose you take this as, so suppose VAN is V angle 0, VBN as you understand is same magnitude but delayed by 120 degree. So if I do VAB, which is VAN minus VBN, so this is, okay, so this is V angle 0 minus V angle minus 120 degree. So if you do the vector addition, you will get it as root 3V 30 degree. Okay, so you will see that the line to line voltage is magnitude is root 3 times the phase voltage. This is all I'm discussing for the star, remember. Okay, of the star, for the star winding. And the, you can see the phase angle is 30 degree leading for the line to line voltage, and whereas the line current is same as the phase current. Okay, because here we do not have anything, so line current is same as the phase current. So I line is same as I phase. Now coming to this delta winding, for delta winding we can see that the line to line voltage, which is line to line voltage, and phase voltage is same. So here we have line to line voltage same as V phase. However, this line current and phase current, they are related like this. Okay, so I line is I phase by root 3. Okay, oh, sorry. So I am writing the things everywhere wrong. Okay, did anyone notice? Oh, this is not going. Okay, so here it was not here, it is here. Okay, like this. V phase is V line to line by root 3. I wrote it in the other way. Okay, so here also this I phase is basically I line by root 3. Okay, here also you can do the same phasor calculation, and you will see that this I, basically if your I phase is I, huh, then if you do like this, in the same way you can do, you can calculate, like if suppose in this winding the current is IA, in this winding IB, in this winding IC, so you can apply the KCL here, and if you apply the KCL and you do the properly like this, so you will get that this I line is root 3 I by 30 degree. So this is also leading by 30 degree. Okay, so in each of the phases, so VAB is leading the VAN by 30 degree, VBC will lead the VB by 30 degree, so VBC will be like this. Okay, so you will see that the VBC will be root 3 V 150 degree. Okay, because your VB is V 120 degree, so it is leading the respective that VB, this corresponding phase by 30 degree. So there is a corresponding lead by 30 degree. Okay, so just try to understand in that way. Okay, so enough of this discussion, so let us go back to our vector groups which I was discussing. So is there any doubt on this page? These are very basic things. Okay, these are discussed in fundamentals of electrical engineering course in first year. Okay, so is there any doubt here? Okay, so let us come back to transformers. Okay, so here I am drawing the, what you say, the Y6 group. Okay, so let us draw the Y6 group. So, okay, so here in the transformer, this is what was happening. Then this is the voltage ratio. Okay, now the power, this is SHV. Okay, so SHV is root 3 VI. Okay, because this voltage is suppose V and this current is I. Okay, so we can calculate, like, so if this current is I in each of the phase, so this is like this, and SLV you will see will be like this. Okay, so SLV will be root 3, because there is a transformation ratio, so it will become V by 80, and there is a transformation ratio in the current also. We have seen this in the single phase transformer also, right, that there is a transformation ratio in both voltage and current. So you will see that the power on both HV side and LV side is the same. Okay, this is the same thing which we have seen even for the single phase, what you said, this thing. Okay, so here in this diagram, the single phase power is V by root 3 I. Okay, and three-phase power is root 3 vi. 3 times of this v by root 3 into I. So you will get the, because this is what v face into I face. Now v face is v line to line by root 3 into I. So you have v by root 3 into I. And if you take 3 times of the single phase powers, so you will get the 3 phase power. So if I multiply 3 in this, so this becomes root 3 into vi. Okay, like this. Okay, now let us go to the other vector group, which is y by 6. So this is y y6 vector group. Okay, so as per our discussion, here also I will take the A terminal from A2. Okay, line A terminal from A2. So this is A2, this is A1, this is B2, this is B1, this is C2, this is C1, this is the neutral. Okay, so now here these are the dots like this. So this is, so let us see what are what. Okay, so this is B1, C1, and this is A2, B2, C2. Now I am not shorting. We will first see um, how to basically what you say, how our vector group is, and on the basis of the vector group we will decide how to connect this. Okay, so first I'm drawing the vector group of this high voltage winding. So on the high voltage side we have seen that this has to be at the 12 o'clock position, right? This A phase, this VAN has to be at 12 o'clock position, VAN at 12 o'clock. So this VAN, which is AN, you see AN, this is BN, this is CN. So AN is at 12 o'clock position. Okay, so AN I am drawing at 12 o'clock. So this is A2, A1, B2, B1, C2, C1. So you can see that here in this diagram, A1, B1, C1 in this vector diagram are shorted as similar to this actual diagram. A1, B1, C1 are shorted. Okay. Now, this is the position. Now I have to draw the, what you say, this y by 6. Now y by 6 means what? This is the situation, right? So this is suppose VAN. So the small VAN should be like this. So that this is at, if this is at 12 o'clock, this is at 6 o'clock. So that this becomes y by 6. 6. It is a 6 o'clock position. Okay. So for this to happen, this, what you said, this phase, this vector direction, it has to be downwards. So it is like this. Okay, now this is your A2, this is your A1. Okay, you just see something I have done very peculiar. What I have done, see, if I have taken A2 and A2 upwards and A1 downwards, here also I'm repeating the same, that A2 and A2 should be upward and A1 should be downward. Okay, this thing I have maybe written that VA2 A1 is in phase with VA2 A1, means that if A2 A1 is in that way, that this A2 A1 is like this, so this A2 A1 also has to be in the similar way. Okay, now similarly the C1 C2 has to be in the similar fashion. So it is something like this. So this is in the same direction, you see, this is parallel to this vector, and this is the location of C2 C1. What about this? This has to, this B1 B2 also similar way has to be parallel to this, and the naming also should be like this, that the B2 is the downward side, B1 is on the upward side. So you see, when I followed that, automatically you see the vector diagram is telling you to short C2 A2 B2, so that this becomes a three phase diagram. automatically it happened. Okay, so that is why these rules are important. It means this va2 a1 should, you should take this diagram basically. If you this a2, if the a2 is up, a1 is down, so you have to draw it in this way, that a2 should be up and a1 should be down. Okay, similar way, when you are drawing in this way, so b2 should be b2 should be like what you say up, basically b2 is on the downward side, and then b1 is little bit upwards. Okay, so here also I have drawn it like this, that b2 is like this and b1 is downwards. So I have to do it in such a way that this, so you will see that automatically the diagram will tell you that you have to short this a2 b2 c2. Okay, so this is what is happened. So the diagram itself is telling you to short the A2, B2, C2. Okay, so this is how I have shorted. So this is the short I have created. So in this way, this is the YY6 group. Okay, so in similar way, you will do the DD0. So let us do the DD0 group. So DD0 and DD6 I will discuss, and then I will discuss the one of the 30-degree groups. Okay, that you can extend to other 30-degree groups also. 30-degree groups are tricky, so I will draw maybe one or two 30-degree groups, and then we will see the questions this week. Okay, now let me draw the DD0. So how will the DD0 look like? So as I said, I'm taking the line terminals at A2, B2, C2. This is A1, this is B1, this is C1. Okay, so for now, let me take it in this way. Okay. Okay, so for DD0, so I will show you how the vector diagram itself will tell me how to connect this. Okay, so this is A2, B2, C2. This is A1, B1, C1. Okay, now I'm not connecting it. First, I will draw the vector diagram. Okay, so how to draw the vector diagram? Okay, so I will show you. So here you see, I will be drawing the, you see, this is basically what? So this is the A, right? This is A, this is B, this is C. So first I'm drawing this because this VAN has to be at 12 o'clock. This is A2 and B2 C2. However, you see here but I'm not writing this as A1, B1, C1. Okay, because this is not a star connection, right? Now how it is connected? Okay, so this B2, you see, B2 is connected where? B2 is connected to A1. So B2 and A1 has to be together because B2 and A1 are shorted here. You can see, right, that B1 and A1 and B2 are shorted. Similarly, B1 and C2 are shorted. So here we have B1 and C2. Okay, and what about A2? A2 is shorted with C1. So here has to be C1. So how this is the actual vectors are like this. Okay, so actual vectors are in this way. A1 to A2. Okay, B1 to B2 and C1 to C2. Okay, so actual vectors, which is this A is here, B is here, C is here. because A is between A2 and A1, and A1 and B2 are shorted, so A1 and B2 are shorted. Then B is between B1 and B2, B1 and B2, where this B1 and C2 are shorted, so B1 and C2 are shorted. C is between C2 and C1, where this C1 is shorted with A2, so C1 is shorted with A2 and C2 is anyway shorted with B1. Okay, so this is how the vector diagram of this delta winding looks like. Okay, now let us draw the vector. So because this is, so this in between that inner phase, basically when we are seeing for the delta binding and when we are seeing this dd0 or dd6, we are seeing this inner, this angle. You see this in how in the star winding we were comparing this, what you say, this kind of the structure. Here also in the delta also we will be what you say, comparing the dotted one. You see the dotted lines here, right? Dotted lines one. So we will be comparing the dotted line structure here. So first I am drawing the dotted line structure. So here the dotted line, because on the upward, on the terminal side, I have to take A2, so that this A2 and N are in phase with, because this is 0, right? So this A2 and N also has to be in phase with the capital A2 and N. Similarly, B2 and N should be in phase with capital B2 and N. Then capital, the small C2 should be in phase with capital C2 and N, like this. Now here also, because this is like this, so A2 is here, so A1 is naturally downwards. Because this direction A2 A1 we have to maintain, right? We have seen that this A2 A1 we were maintaining, A2 A1 also we were taking in phase. You see this rule, VA2 A1 is in phase with capital VA2 A1. So basically this A2 A1 vector has to be in phase. So here, so this A2 A1 vector is on the side like this. So okay. So A2 is up and A1 is down. So this A2 should be here and A1 is down. Okay. Then B2 B1 has to be in phase for this B group. So B2 is here. So B1 has to be here, because this is the vector like this, right? A2 A1 vector is like this. So here also A2 A1 vector is like this. So this vector and this vector has to be in phase. Similarly, B1 B2 vector will automatically come in phase. If you have made one vector in phase, and other vector will automatically come in phase. Okay, now here also this is like this. Okay, so this is C2 here, so C1 has to be upwards. So this is telling you to connect uh, A1 with B2. So let us connect A1 with B2. Okay, let us connect A1 with B2. So here it is like this. Then it is telling you to connect B1 with C2. And then it is telling you to connect C1 with A2. Okay, like this. So this is how this diagram looks like. Okay. And here the terminals are here, A2, B2, C2. Okay. Now I'm not drawing the DD6 one because it is easy. I'll be drawing YD1. Okay. Because YD1 is a little bit tricky one that you can extend to others also. Okay. So let me draw the YD1 structure. So YD1. So first I'm drawing the star winding. Okay, like this. And here A2, B2, C2 are the terminals, and this A1, B1, C1 I am shorting. Okay, because it is said, right, the line terminals are A2, B, at A2, B2, C2. For this line A terminals for the HV side is from A2. Okay, so this is for HV side. So this is like this. Now here I am drawing the delta winding part, but I'm not connecting it because I do not know in what way to connect. Okay, I do not know, so I'm not drawing it. Okay, it's like this. So how to connect my delta winding depending on this vector group? So let us see. So first of all, this is my HV. This is the LV. It is at 1 o'clock position. So this is 30 degree. Okay, this we have seen in the beginning of the class. Now, let us first draw the star winding one. So this is the star winding. So here A2, A1, B2, B1, C2, C1. Okay, so this is the situation. Now, what is the so here what we have to do? We have to draw in such a way that this windings basically first of all what we have to follow, we have to follow that we A1 A2 is in phase with V A1 A2, small V A1 A2. Okay, so this is like this, so it has to be in this way. Okay, so this is A2, this is A1. Now in what way I, because you try to understand my because I have drawn it in this way, so whatever what you say, this phaser will be there because I will be seeing the LV side phaser, right? It will be pointed at A2. So it will be either pointed like this or like this. So, but what we want this phaser to be in such a way that it becomes 30 degree to this side, right? So we want the phaser to be in this way, right? We want the phasers to be in such a way. So this is A phaser, this is the B phaser, this is the C phaser. So this phaser in the internal phaser of the delta winding, depending on this vector group, has to be in this way, right? So this is my reference phaser, which is the AN. So my small AN has to be like this. Okay, like this. So this small an the reference internal, because see here for the delta windings we were seeing the internal phasors, right? So it has to be in such a way that this basically lags by 30 degree. Okay, this is a 30 degree lag group. YD1 is a 30 degree lag group, right? So as I discussed, you people who have joined late, you can see very early I was discussing these notations. Okay, what are these notations? Okay, so you can see the recorded lectures. Okay, in the beginning of the lecture I've discussed that. So it is like this. So it is like this. Now you know that the B phaser is how? So this B phaser, so this is A1. Now see, this B phaser is coming down like this, right? So you know the for this B phaser how it has to be? It has it first of all this has to be parallel like this. So I will draw parallel like this. Okay, and we know that the B phaser should have B2. So I'm drawing the B2 here. And you know that this B1 B2 has to be in phase. So this B1 B2 has to be in phase. Okay, so this B1 B2 are in phase. Is it not? So this is A. So you can see that this A1 has to be connected to B2. So this you from this diagram, A1 has to be connected to B2. Okay. And what about this? So this is the C phaser. Now we know that the head of the C phaser we have C2. So this C2 is like here. So C2 and C1 has to be co-phasal with this capital C2 C1. So this C2 C1 is like this. Okay. So this is C2 here and this C1 is here. Okay, like this. So you can see that this C1 is connected to A2 and C2 is connected to B1. So C2 is connected to B1 and C1 is connected to A2. So this is my YD connection. Now, in case you have doubt, I will draw the YD11 connection also. Okay, so that it is more clear. Okay, so actually for this today's week assignment questions, only this slide is enough. Okay, only this slide is enough. here this 30 degree is there, that this I have told additionally and derived it additionally, but only these boxes are enough, okay, to solve this assignment. But I'm discussing the other things also because it will help you in future also, okay, not only in this class, it will help you in future also in case someone asks you what are the vector groups and all. So that will help you, okay. Now let us draw YD11, okay. So first of all, I am drawing the, so in case you have doubt, you have, don't hesitate, okay, do not hesitate, because it is important to learn these things properly, right? You have doubt in the procedure, or if you have doubt in anywhere, you stop and ask, okay. Because if you are good in this, you can practice this, maybe you can read it from Nagrath Kothari, okay. This, they have discussed the vector groups in detail. Now, if you master this now, they will give you any connection, like you can draw the connection diagram, okay, and you can easily tell, okay, this connection is like this, so this is 30-degree lag or 30-degree lead, what is happening between the this phase voltage and this phase voltage, how they are leading or lagging, you can tell, okay. So you can also see the this recorded lectures also. In the recorded lectures also, these things are discussed, okay. So here I am shorting this because my line terminals are at A2, okay. Now here I am just drawing the delta windings. I'm not connecting them, okay. Actually this thing, you can see, okay, so let me just draw it here, okay. So this is like this. I do not know how to connect this unless I draw the vector diagram, okay. So first I'm drawing the vector diagram for star, okay. This is A2, A1, B2, B1, C2, C1, and this my A location is here. A phaser location is matching with A2, okay. Always, in all the cases. In all the cases here also, even for this also, this is like this, okay. It should match with A2. So my A is here, my B is here. B should match with B2, C should match with C2, okay, like this. And this is C. Now I have to draw it in such a way that this is at YD11. 11 means if this is my reference, HV side reference, so my LV side has to be here, and there has a 30-degree lead, okay. So it is like this. So you see one thing, that, so first of all I will draw the A2 A1. So here also this A2 A1 has to be in phase like this, right? So this is the situation, and this is the location of my A phaser. Now how should be this A phaser, so that it is basically leading by the this eight this reference by 30-degree, okay. So one option is that my A phaser is coming in this way, and one option is my A phaser is coming in this way. So if my A phaser is coming in this way, then only it will lead by 30-degree, okay. So my diagram will be made here on this side of the paper, not on this side, because you see in the previous case, because this was lagging, you see this, if this is my reference, so this was lagging, but this should lead, so I have to draw it in this side of the paper, okay. Just first match it, okay. First you draw both the possibilities, and then you see, okay, that how to proceed, in which direction to proceed. If you proceed in this direction, then it will be in this YD1, okay. But in this direction we do not have to proceed, we have to proceed in this direction, okay, our diagram. So let us erase this. So this is the direction in which I have to proceed. So this is in this way. Now wherever there is A1, there has to be B1, basically not B1, because this is A phase. So my B phase is like this, right? So this is A, then no, this is B. This is B, and this is C phase. Okay. So this is the situation. So this is my A phase, and this is the B phase. Okay. And this is the C phase. Now, where is the C phase? There has to be C2, right? So this A1 has to be, so this, we know that this this is like this, right? So on this side there has to be C2, because this box thing I mark wherever there is B2, A2, C2. So here also this has to be C2 and this has to be B2. Okay. So I have to put the vector diagram in such a way that C2 comes here. Okay. This is A1. So this A1 is connected to C2. Then you see this has to be B2. So, and also you have to follow this. You see, A1, A2 is like this. C2, C1 is like this. So this has to be C1. You can see that C1, C2 is in this way. It is co-facial with this. Actually, I'm drawing it a little bit bent because I did not, I'm not drawing so nicely. But you can understand that this is co-facial with in this way. Okay, this is co-facial with this C1, C2, with this C1, C2. Okay. Then here, this is how I will draw this. Okay. So you see A2 is connected to B1. B2 is connected to C1. And C2 is connected to A1. So this is the diagram for YD11. Okay. So I have discussed a lot on this vector group. So if there is any doubt, you ask me. Then we will proceed with the assignment. For solving the assignment, you need only this page. Okay. These things are not there, but I just discussed for your general information. Okay. Because we're discussing the three-phase transformer. So I thought I'll discuss this. Okay. So now let us see the questions if there is no doubt. So these questions are very simple, okay? Very simple questions. But before going to these questions, I will discuss one very basic things which are related to this star, basically this star delta connection, okay? So in the star delta connection, I want to discuss. So it is generally recommended uh, to use star connection on HV side. Okay. Basically, high voltage, low capacity. Capacity means current capacity. Okay. Applications. Whereas a delta connection is preferred on LV side, low voltage, high capacity application. Okay. Okay. So that is the thing. Okay. Now there is one exception, however. So you will see that this in view of this, the Y delta, basically Y delta means Y is on the primary side, delta is on the load or secondary side. Connection is used for step down connection is for stepping down, and delta by connection for stepping up. There is just one exception, that what you say, suppose in distribution side, okay, like in our homes, basically we have the transmission level side and then we have the distribution side which is connected towards the load. Now you will see that because in the distribution side in our homes, you will see that there are three phase loads also, single phase loads also. So what needs to be done, that even though the distribution side or low or is on the low voltage side, like our homes have 440 volt supply, right, but the transformers which are basically using for stepping down, so the voltages which are coming are at suppose 11 kV, and then they are used for stepping it down to 400 volt level. Okay, so you see they are used for stepping down, but still in those applications we use the star connection on the low voltage side. Okay, because on the star side we will be having the three, what you say, individual phases accessible. So for that, what is done is that on the distribution side this rule is not followed. Okay, so this is the exception of the distribution loads are the exception of this above rule. Okay, and there are various other exceptions also, but you will see in while solving the questions, this is valid. Okay, unless specified, this is default unless specified in the questions very clearly. So distribution load is the exception. Okay. Now let us see the questions. So this is the question. So this is what they have given us the data. So here what is the data? The HV side voltage is 11 kV. The HV side current is 10 ampere. And the voltage ratio, this transfer per phase turns ratio is 14. Okay. So here, so what is the situation? So this, let us write these things down. So VHV line to line is 11 kV. Then this I line current on HV side is 10 ampere, and this per phase voltage ratio, basically VHV phase to VLV phase is 14:1. Okay, now it is said that the estimate the LV side line to line voltage if the transformer is of Y delta side. So you see they are saying that Y delta side is like this. So there's, so in this notation, basically if you see this is the notation. So if it is written as Y delta, so it means HV LV. If I mean delta star, so here also the HV side is delta and the LV side is star. Okay, so you see even in these diagrams also, when I was writing this Y by 6, so I meant this primary winding to be HV, right? So here also in the questions also you have to follow that the first winding type, this Y winding type, they're indirectly saying that this is HV, and this delta winding they are saying this is indirectly LV. Okay, similarly here also if they would have didn't given it in the reverse way, like delta Y, okay, then you have to take this primary side to be HV and the secondary side to be LV. Okay, this is the notation which is generally followed. That is why I discussed these notations. Okay, this is the British code, so I discussed this. Okay, that is why in the beginning of the class. So this is the situation. Now this is the HV side in the question. Okay, so and this is the LV side. Okay, so they are telling us to find the LV side line to line voltage. Okay, so this is the 11 kV voltage. So first of all, VHV, which is star side. So star line to line voltage, star side line to line voltage is 11 kV. Okay, so this is V line to line star side. Now what will be V phase star side? So V phase star side we have discussed, right? That what is the relation between the phase voltage and line to line voltage for a star connection. So phase voltage is line to line by √3. Okay. So here this phase voltage is line to line voltage by √3. Now this ratio, This ratio is in the phase voltages. We have seen that this ratio N1 is to N2 is the phase voltage transformation ratio. By default, this is phase voltage transformation ratio unless specified, okay, in the question. So you will see that they have specified also phase voltage ratio, phase turns ratio, okay. So what we need to do, so this 14 is to 1 is 11 kV by root 3 by V phase delta. Okay, so we can calculate what will be the V phase on the delta side. So this will be 11 kV by root 3 by 14. Okay, and we know that for a delta winding, which because you see delta side is the LV side. Okay, so delta side is the LV side. So they're asking us line to line voltage on the LV side. So we have gotten the phase voltage on the LV side or the delta side. And we know that for a delta connection, line to line voltage and is equal to phase voltage. So this is V line to line is equal to V phase delta, which is 11 kV by root 3 by 14. Okay. So is there any doubt in this question? This is assignment is very simple assignment. Okay, it's a very simple straightforward assignment. If you understand this slide on, if you understand this slide only, you will be able to solve most of the questions in this three phase three winding transformer. Okay, these things I have just discussed extra. Now let us go to the next question. Now in the next question, what we have to calculate? We have to calculate the LV side line current. Okay. Now this is again this is Y star star delta. So this is HV side to LV. Okay. So HV is star, LV is delta. Now they are telling us to calculate the line current on the LV side. So how to do it? Okay. So this you see HV side line current they have given as 10 ampere. So HV side line current is 10 ampere. And we know that the line, see here also the ratio, the transformation ratio which we are talking about, it is valid for phase voltage and then it is also valid for phase currents. Okay, not the line currents. So this ratio is valid for phase voltage ratio or the phase current ratio. Okay, so this you see 80 is to I, this is for phase currents. Okay, so this ratio is valid for phase voltage and phase currents. Okay, so for that, on the HV side this is given as line current. Okay, now what will be HV side phase current? Remember this is star connection, so for star connection what? Same, correct. So this is same, so this is same as HV line current because this is star connected. So this is same 10 ampere. Okay, now we will use the transformation ratio. So now we know that this, if suppose this V1 by V2 is 14, this is phase voltages, remember, this is equal to I2 by I1. Okay, so we need to calculate I2. So I2, which is the phase current on LV side, is 14 times the phase current on HV side. Okay, so this is basically I1. So this comes out to be 140. But in the question we are asked the line current. Okay, now you remember the what is the so this, you remember the LV side is what? LV side is delta. Okay, now in delta connection, what is the relation between line to line current and phase current? What is the relation? So this line to line current is root 3 times the phase current. Okay, because we are asked the line current, so we have to take root 3 times I2. Okay, so this becomes root 3 times I2, which is root 3 times 140. Okay, So is there any doubt in here? Okay. What about other people? Is it clear? Akash, Shiv Kumar Mahato, Shri Vaishnavi, Sambit Kumar. Hmm? Okay. Okay. So it's clear to everyone, right? Okay. So let us go to the next question. Now in this next question, we have to calculate the kVA output. Okay. So you see how to calculate the kVA output. We know the kVA for a three-phase voltage, three-phase system is root 3 into V line to line into I line to line, or 3 into V phase into I phase. Okay, either of the two. So here we are given line to line voltage and line current, so we can directly find the kVA rating. And we have seen that the whether kVA is it on the HV side or LV side, they are the same. Okay, so this is what, this is root 3 times of 11 into 10, very straightforward. Okay, this is the kVA rating, because this is given already in the question, in the data. You see 11 kV line to line, 10 ampere line current. Okay, so this is the kVA rating. Okay, now let us go to the next question. Now you see we have to estimate the LV side line to line voltage of the if the transformer is of delta star type. Now here you see they have put delta on the HV side and star on the LV side. Okay, so now our delta winding is HV and star winding is LV. They have just reversed the thing. Data is same, but they have reversed the thing. Now they're asking us to calculate the LV side line to line voltage or Y star side line to line voltage. So they're telling us to calculate this. Okay, but we are given this V line to line on the delta side, which is 11 kV side. Okay, so this is given to us as 11 kV. Now we have to find V line to line on the LV side for this question. So how to do it? So first of all, we will because we want to go from one side, one winding to other winding, we will need the transformation ratio. Now in this transformation ratio, we need phase voltage, right? So we will start with the HV side. We know HV side line voltage is 11 kV. Okay, which is on delta side. Now for V line to line, delta is same as V phase delta, which is 11 kV. So V phase delta is 11 kV. Now what is this ratio? This ratio is V phase delta, which is HV here, divided by V phase star, which is LV. So what is this ratio? It comes out to be that V phase LV, V phase star is 11 kV by 14. Okay, this is 14 by 1. So this is 14. Now we have to calculate the line voltage. So line voltage of the star is root 3 times phase voltage of the star. So this is root 3 11 kV by 14. Okay, this is how you will solve for this question. Is there any doubt here? Okay, this assignment is this only. Okay, they have asked these types of questions only. Okay, just do not do silly mistakes, otherwise you are just read the question and always remember that this first connection is HV, okay, and the second connection is LV. Then you proceed, then you follow the data, and then you see whether it is star connection and delta connection, and remember this slide. Remember this slide, then you are good to go, and do not make any silly mistakes. Then you will be easily able to solve these questions. Okay, now here what we need to do, we need to calculate the LV side line current. Okay, so here I line they have given for HV side, which is the delta side. So I line, so first of all I'm writing this is HV, star is LV. So I line on the delta side, they have given it as 10 amperes. Okay, now because this is I, so what will be I phase delta? I phase delta will be I line delta by root 3, which is 10 by root 3. Now we will use the transformation ratio. So what is this transformation ratio? This will be I LV by IHV phase, remember. phase. ठीक है? So I phase star by I phase delta. So what about I phase star? It becomes I phase delta into 14. So this will come out to be 14 into 10 by root 3. And phase current and line current is same for the star connection, because they're asking us the line current on the LV side. So this is basically 14 into 10 by root 3. Okay. So these are simple questions. Okay. So I'll not ask the again and again if you have questions. If you have questions, do not hesitate to stop me in between. Okay. Just stop me in between if you have doubt. So this is how we will proceed for this. Now we go to the next part. In the next part, again, we have to calculate the KVA output, even if it is of, if whether it be of delta side, delta star or star delta, the KVA remains the same as long as this volt line to line voltage and line current remains the same. So the KVA for this part also is root 3 V line to line V into I line. So this is root 3 into 11 kV into 10. You can calculate it from the HV side or LV side. You will see that it will be the same. Okay. We have seen this in the very first slide. Okay. That this is the ratio. So this, you see this SLV same as SHV. Okay. Now let us go to the next question. Now in the next question, what it is said is that this is a three-phase delta star transformer. So you see they are writing delta star, and while showing the notation, they have shown the HV side here. So the first connection is HV connection. Okay. So this is the, what you say, this notation they follow. Okay. So they are saying that it is feeding the power to a 20 kilowatt 415 volt three phase load with 75% efficiency and 0.7 power factor. Okay. So what should be the minimum KVA rating of the transformer? Okay. So on the star side, they have connected the load like this. So this is like this. Now here you have the, okay, star connection. So here they have connected it to a three-phase load. So this is a three-phase load. Okay. So this power is 20 kilowatt. But you see the transformer, this is, but the power factor of this load is 0.7 power factor, and the this efficiency of this transformer is 75%. Okay. So first of all, let us calculate the KVA of this three-phase load. So what is the KVA of this three-phase load? So we know that VI, so this is for single phase, it is VI cos phi. For three phase, it becomes root 3 VI cos phi. Okay. So root 3 VI cos phi is your active power. You remember the power triangle which I discussed in the second assignment. So there I have discussed whatever I have discussed, you just multiply it by root 3, it becomes the same thing. Okay. The active power is root 3 VI sin phi. This is in watts. This is in VAR. And root 3 VI is apparent power. Okay. This is in VA. So basically, whenever we are talking about the VA rate, we are talking about the VA rating of the transformer. So what we need to do, we first need to find the VA rating of the load. So how we will find the VA rating of the load? We will just use this active power formula. So what is the active power? It is root 3 VI into cos phi, which is how much it is given. It is given as 20 kilowatt. Now, because we are interested in VA rating, so this is the VA rating. So VA rating becomes root 3 VI becomes 20 kVA by cos phi. Okay, so this is the VA rating. So this is 20 kVA by 0.7. So this is the VA rating. Now, remember that the transformer efficiency, which is the output VA by input VA, is 0.75%. Okay, 0.75. So, okay. So this is the scenario. Now what we have to calculate is we have to calculate the basically VA input VA rating, because input VA rating is the more because that is the maximum rating. So that what is the maximum VA this transformer should have, so that it can supply the output VA of this 20 in 20 kVA by 0.7. So this is the load VA or the output VA, because out at the output of the transformer we have the load. So this is same as output VA rating. Okay, so this output VA is 20 by 0.7. This divided by input VA is 0.75. So basically the input VA or the VA rating of the transformer. Okay, so the VA rating of the transformer becomes 20 into 10 power 3 by 0.7 divided by 0.75. This becomes the input or the VA rating of the transformer. Okay, so this is how you can calculate. Is there any doubt here? Okay, so let us go to the next part. Yes, you have doubt? Oh, okay. So let us go to the next question. Now in the next question, what we need to do, we need to calculate the line current in the HV side. Okay, so what will be the line current in the HV side? Now you remember that see, when in a transformer it is written like this, right? That 11 kV is to 1 kV transformer with this much of, so generally the transformer you will see it will be written like this, like 3 kVA 50 hertz. So this 11 kV is V line to line high voltage by V line to line low voltage. This is the VA rating of the transformer and this is the frequency of operation. Okay. So this is how a transformer, what you say, ratings are given. If you will see at the transformer, you will see there will be a nameplate. So in the nameplate, there will be a rating like this. So in that nameplate, this voltage is line to line voltage. Okay. So this is the, in the nameplate, you will see this is the line to line voltage given for the transformer. Now, but you remember that the transformation ratio, which is this 80, is phase voltage. Okay, so this is in phase voltage, high voltage by phase voltage, low voltage of side. Okay, like this. But this notation is on line to line voltage basis. Okay, so here what we have to do is we have to estimate the line current in the HV side. Now remember, we have already calculated the VA rating of the transformer. So you see this much is the VA rating. Okay, after doing all this, we have gotten the KVA rating of the transformer. Now what we need to do, we need to calculate the line current on the HV side. So you remember what is the what is the S, what you say S HV side? So HV side is root 3 V line to line HV by I line HV. Okay, root 3 into VLL into IL, or 3 V phase into I phase HV. Okay, this is the situation. Now we have calculated the KVA rating, whether it be on HV side or SV side, it is the same. This is the KVA rating which we have calculated from the previous question. So this is 38 point something, right? 38 kVA. So this is 38 kVA. So here we have to calculate the line current on the HV side. Now we know from the nameplate reading the voltage rating on the V line to line on the HV side. So V line to line on the HV side is 6600. So this 38 kVA is root 3 6600 from the nameplate reading. This is the nameplate reading. Okay. Into I line. So I line we can directly get line current. So this will be 38 kVA by root 3 into 6600. Okay. So is there any doubt here? You can see that this assignment is pretty simple assignment. Okay. Now we go to the next question. Now in the next question, we have to estimate the phase current in the HV side. Okay. Now remember this is the line current on the HV side. This is the line current on the HV side we have obtained in the previous question. And what is the HV side? HV side is the delta connection. Okay. So HV side is delta. And for delta, what is the relation between the phase current and line current? Okay. And from the previous question, we have obtained the line current value. So this value we have obtained. So this value is something like 3.33. So this you do 3.33 by root 3. Okay. This one will give you the phase current on the delta side. Okay. Delta side or the HV side, because HV here is the delta. Okay. Now we move to the next question. Now in the next question, we have to estimate the line current in the LV side. Okay. Now in the LV side, we do not care. Okay. First of all, this SV sorry, KVA rating on the HV side is same as the KVA rating on the LV side, which we have calculated in the first question of this parts. Okay, so this is 38 kVA. Okay, now this is equal to root 3 V line to line LV I line LV. Okay, now from the nameplate reading, what we have line to line voltage on the LV side, it is 415 volt. So we can directly calculate the line current. Okay. So this line current on the LV side, we can calculate directly. Okay. So this is how we can calculate. Now we have to calculate the phase current in the LV side. Now what is LV? LV star. And we know that for the star, the I line star is same as I phase star. So I phase star is same as the previous question. Okay, same as this value, 38 kVA by root 3 415. Okay, so that is it for this week's assignment. So is there any doubt? If there is no doubt, then we will stop the class here. Okay. So these are very basic questions. Okay, very straightforward, simple questions which you can do. Okay, just do not do silly mistakes. Okay, do not do silly mistakes, then you will be able to solve these questions very easily. Okay, so that is it. Yes, yes, I can hear. Can you tell? You're telling something. Seventh question. Where is the seventh question? Uh, huh. Okay, so here. No, they're asking. See the kVA rating of the transformer. When we talk about its input, its kVA, right? We're not talking about the output side kVA, because see, when we say like this is what you say, this is supplying some load, but the transformer is having low efficiency, but in order to supply this transformer, you will need to give it that much of amount of input power, right? You have to give it that much amount of input power, otherwise this transformer will not be able to give it the load. Okay, so that is what they're asking you to tell the minimum amount of in, because that much only is the actual kVA of the transformer. Okay, its efficiency is poor, so it is giving output low, but when we are talking about minimum required kVA rating, we mean to say the maximum, basically the kVA which it needs to supply this three-phase load. Okay, this kVA which this transformer is taking to supply this three-phase load. Okay. Yes, yes, yes. That will be the same, because we have seen, right, the SLV or SHV remains the same, whether we energize it from the LV side or whether we energize it from the HV side, it remains the same. Okay, because you see SLV also we got the same thing, and SHV we also got the same thing. Okay. Yes, yes, yes. Hmm. um Actually, you see, that is true, because in general they have given it a very poor efficiency, but this efficiency is generally like 98%, 99%. So that is why we generally take this thing that okay, shv is approximately same as slv, okay, like this. But here they have, for the question's sake, they have given it like this, okay. Okay, so okay, so is there any more questions? Okay, okay. So that is it. If we do not have any more questions, then we will stop the what you say class here, and then we will meet in the next class. Okay, in the next class we will have some other topics, and then we will go through it. Okay, so that is it. If you do not have any doubt, you can maybe leave the session. Okay, okay then. Okay, so I'm stopping the class here today. Okay. Okay. Okay then, thank you. I am also leaving. Okay, in case there is no other doubts. Okay then, so I am also leaving. Okay. Hmm. Okay then.